Hello, my name is Derek Rogers, and I'm from Stress's Cincinnati office. And joining me in this presentation today is John Norris from our Houston offices. Today, the title of our presentation is Safety and Reliability from Turnaround to Turnaround. Through the years at Stress, our focus has been supporting our customers' ability to get from turnaround to turnaround safely and reliably. Let me make sure I say this first. We Stress understand the importance of safe operations and make that our #1 priority when supporting our customers. In our review processes and when on site with condition assessments, we understand the high risk involved. Whether a customer is in the planning stages of a turnaround and developing the scope, or just found an unexpected anomaly and needs to determine whether they can run safely to the upcoming turnaround, or they need to come down for repair. We support their efforts in evaluating both of those scenarios to understand the risk associated with each and develop a cost-effective plan for mitigating failure. Throughout this presentation, we'll outline Stress's resources and capabilities that enable us to evaluate critical components to determine how long they can operate safely and reliably in a given environment. Stress's capabilities range from material evaluations to full-scale testing for validating materials, to computational analysis to simulate the component under a set of operating conditions. Many of our customers in today's environment are pushing their turnarounds out and opting for reduced schedules to minimize the impacts on budgets and profitability. Stress has been able to help customers assess the rate of damage to critical components, determine the remaining life so they have a basis to make informed decisions whether to come down now or delay the repair for a scheduled opportunity. We work with the customer to develop an inspection strategy and outline the information needed to quantify if the component is safe and reliable to operate for an extended period of time. If the component is high risk, we provide the run repair options for the customer. Those assessments which quantify the rate of damage also help customers minimizing unexpected, unplanned, and unscheduled activities by providing them with predictions on time to failure, supporting their efforts in determining which components are high risk, and developing a plan for repair or replace on planned schedule. Stress has been providing physics-based insights for clients for over 48 years. We got our start in the power generation industry, specifically nuclear, providing stress certifications for piping. As the nuclear industry began to slow down in the 70s, we moved our skill sets over to the oil and gas industry. Over the years, we have expanded into over 15 different industries, ranging from power generation, oil and gas, pharma, consumer products, aerospace, rail, and medical technologies. The physics are the same throughout all of these industries. As we have expanded the industries we are serving, we continue to invest in our ability to deliver value to our customers. And by participating in many different industries, we're exposed to many different problems, materials, and technologies which enable us to transfer technology from one industry to another. An example of technology transfer would be how we utilize the skills developed in our lab performing full-scale testing, such as custom sensor design, data acquisition, and digital twin modeling to measure the G-force exposure during manufacturing and shipment on vials of biologics. This biologic was unable to experience excessive G-force, so we designed a sensor the size of a dime that could fit into a vial to measure force to validate handling precautions. Later in the presentation, I will show you a picture of the sensor and the vial. This is an excellent example of how we took technology from the oil and gas market to the pharmaceutical packaging market. I could go on outlining how the work we're doing with threaded connections for risers enabled us to solve a difficult problem on a dishwashing detergent bottle that got us into the consumer products industry. But I won't, as I know we have a minimal amount of time today. So now I'll pass the mic over to my colleague, John Norris.
Thanks, Derek. SES can provide design and data reviews, and if necessary, even pre-assessments of critical equipment to better prepare for issues and findings during turnarounds and other scheduled outages. Many times, these assessments can be used as technical basis for changes in the required inspection intervals. These assessments can range from advanced modeling, such as finite element analysis, computational fluid dynamics, digital image correlation, on-site loading and temperature measurements, to more routine code calculations to verify minimum thicknesses or maximum allowable pressures. Having the bulk of the assessment developed before the heat of the moment allows for better decisions during the critical time. Other options are to utilize the downtime for additional data collection, such as dimensional checks and measures or other material sampling to finalize or refine the model and subsequent assessment results. Despite the best plans and interactions, invariably something unexpected may still come up. SES, with our multidisciplined staff, can assist in analyzing and assessing these run, repair, replace decisions in a timely manner in order to reduce the overall impact to the outage schedule. Mechanical integrity is a broad term applied to the assessment of equipment to verify its safe and proper operation. In pursuit of this, SES routinely provides the following, as well as other assessments to evaluate the mechanical integrity of equipment and components. Evaluating the minimum thickness for towers, exchangers, and piping. Since this generally is not a one-off value, these results, with all the loading considerations, can sometimes be deceptively complicated. Characterizing damage and performing fitness for service activities. The methods and acceptance criteria are fairly standard throughout the industry. However, the accuracy and applicability of the damage characterization, as well as bounding of the unknowns, can make a big difference in the results, conclusions, and the determination in the need for mitigations or other actions. Checking the structural stability during maintenance or repair operations. Examples include, but are not limited to, access openings and stability during post-weld heat treatment. These types of assessments need not only consider the structural strength, but the potential deformations and their effect on the usefulness of the components after completion of such activities. Considering the effects from process or heat transfer, whether it's consideration of the potential for slug or hammer flow in a piping system, or the expected thermal effects resulting from loss of insulation or refractory. Stress engineering can provide insights to these potential or actual conditions or scenarios. Reviewing and assessing bolting joints, including, as applicable, the effects from thermal transients, in addition to checking stresses, reviewing gasket selections or bolting procedures, how the joints are expected to react to upsets or other thermal transients can also be simulated. Collecting additional field data to validate or improve the precision of equipment models and assessment activities. This could be additional dimensional information requiring measurements or laser scans, material property validation that can be determined from testing of small material samples or collecting strain, temperature, or actual acoustic emission information to determine more realistic loading and specific materials resistance capabilities. Derek has some further details on data collection services we can provide.
Thank you, John. In the opening slide, I discussed how we support customers in evaluating critical components, whether it's for delaying a turnaround or evaluating unexpected anomaly. What I can't emphasize enough is the more accurate the data, the more accurate the modeling and resulting assessments. Typical types of data collection are acoustic emission testing, which provides a global screening of components to detect the active cracking in those components. And this can actually be performed prior to a turnaround or a shutdown in order to detect those active crackings and locate them for further direct assessments during the turnaround. Then there's our scoop sampling. It's the ability to extract material from in-service components to measure the properties of those materials. The scoops can range from about 1 1/4 inches to 3 3/4 inches in width. You can see the two sizes here in the picture. In addition, we've got our rod load measurements, which is used for high energy piping. It enables us to offload a hanger and measure the load in that hanger and determine the high stress areas in those particular locations. Instrumentation, strain gauges, thermocouples. I'm going to talk more about that further in the presentation. But in addition, we've got laser scanning, and also there's digital image correlation, which is the use of optical techniques to acquire strain data. Through the years, Stress has leveraged their expertise in sensor development, data acquisition, and data interpretation. Stress started performing full-scale testing over 40 years ago, and through the years, we have developed significant expertise in those areas. As I outlined in my previous slide on how we transferred that technology from one industry to another, this slide demonstrates well how we took that technology from the shop or in a controlled environment and moved it to the field in a manufacturing environment. Many of you have seen this slide before at this conference. This slide outlines our coke drum health monitoring program, which starts by utilizing a laser scan to define the geometry of the coke drum, and it identifies the high stress areas of the drum. We utilize that information to determine where we will locate our sensors and develop our repair plans for the bulges if needed. The sensors on the drums enable us to determine the rate of damage created by low cycle fatigue and to provide feedback to the operators for optimizing the parameters to minimize the damage. Also, you can see on the slide is a rail car bolster. We have instrumented many cars through the years, and this particular one, Stress measured strains at 94 locations on a vented and non-vented bolster for powered and unpowered trucks at known and potential crack locations and at various mid-plane locations to measure the overall structural response of the frame. We also measured accelerations and displacements of the truck and bolster while monitoring the GPS speed and location. So what you also see on the screen here in the middle is a tire mold. This tire mold, you can see there are 3 sensors in the mold, and what we did was that we developed custom sensors to put in the mold that had 6 degrees of freedom. These molds were being fabricated or manufactured through additive manufacturing, and the sips, which are the joints in the mold or the lines in the tires, if you will, were cracking, and so they wanted to measure the force being applied with the rubber as it pushed into the tire mold. So we had to develop custom sensors for that particular application. At the bottom, you can see is the valves that I spoke about earlier. These particular valves have accelerometers in them. In that particular mid-bottom picture, you can see a quarter on the table, and next to that quarter is a accelerometer that's going in the valve, and that is to measure the G-force or as the valve is passed through or moved through production, manufacturing, but it's also included in the valve as it's being shipped via logistics. So you can see through this wide variety of applications for custom sensing, we've taken that technology and we've advanced it several ways. So on the previous slide, I showed you examples of custom sensors and many different applications that we have used those custom sensors in order to measure such things as force and whether it be those valves or, as I showed, the rail cars. But I want to provide you another example of some other different components that we are measuring and how we have advanced this technology. And what I wanted to provide you here was an understanding of how we've used this technology for condition-based monitoring. As you can see on the screen, these are riser joints, which have a 5-year inspection criteria for being inspected. This is accomplished by rotating 20% of the riser onshore every year to be disassembled and inspected. This requires extensive boat trips and trucking of the risers. There are typically 20 riser joints from each riser system, which are transported on a boat and 1 riser per truck to an inspection facility each year, making the logistics of the drilling inspection very costly. These risers are obviously below sea level. And in that subsea application, these risers are bending much like guitar strings as they interact with the ocean's currents, causing damage at the joints. Because of the cost and time required to inspect these joints, customers needed another approach, which was to move to a life cycle condition-based monitoring and inspection system that could be deployed on a mobile operating drill unit. The new riser monitoring system measures the load at the joints along with in situ drilling information, met ocean conditions from which riser joint fatigue damage would be determined and riser joints identified for inspection. Utilizing this process and incorporating the machine learning, customers were able to experience significant savings in downtime.
Okay, Derek, thank you. Despite the specific industry, the types of equipment is typically consistent. Stress engineering has experience in analyzing and assessing these common types of equipment and their components, as well as the technical expertise to assess the unusual or uncommon equipment types. On pressure vessels, code and other industry rigor gap assessments can be provided to verify code compliance, to determine the acceptability of the current condition, or to estimate the remaining useful life or required inspection interval. Piping flexibility using traditional linear elastic or more advanced elastic plastic modeling can be utilized to verify not only code compliance, but also the localized effects from deformations or changes expected from high temperature exposure. Field verifications, including actual loading determinations on supports and hangers, can be performed in conjunction to maximize the accuracy of modeling activities. The remaining life of tubes and fire heaters provides many challenges from incomplete loading data to uncertainties in material properties. Stress engineering offers the full range of assessment of fired heater tubes, from traditional remaining life determination to specific property determination using our accelerated creep testing facilities. From wind exposure to compromised foundations to damaged components as well, all in combination, stress engineering can provide authoritative assessments of storage tanks. Heat exchangers are a subset of pressure vessels. Stress engineering can assess the traditional TEMA designs, the air-cooled fin-fan coolers, as well as the compact plate and frame type exchangers. Stacks, although similar to process towers, are subject to different acceptance criteria. Stress engineering is familiar with the unique requirements for these assets and can advise on various mitigations and repair options. Storage bins and silos, also similar to process vessels, are subject to differing loading conditions from the internal product. Stress engineering can address these types of equipment and their unique loading. Since one size does not fit all, and a computational solution to the degradation does not always result in an acceptable as-is condition, stress engineering can assist in the conceptualization and validation of unique and specific repair mitigations, clamps, and/or enclosures following the requirements of ASME PCC2 or other typical RAGA-GAP for these types of solutions. Mechanical assessments of the typical process equipment can run the full range from verification of code and fabrication rules to advanced modeling such as finite element analysis and computational fluid dynamics to full-scale destructive testing. Whereas the traditional code formulas and approaches address design for a specific purpose, the use of these advanced techniques better quantify the actual loading and material responses, therefore allowing for an assessment of a seemingly degraded or compromised component, and allows us to better quantify the reduction in margin, if in actuality any, from the original design basis. Stress engineering has full-scale testing at 3 locations in the Houston area, as well as high temperature and non-metallics capability in the Cincinnati office. Just a few examples of testing services that stress engineering can provide. In addition to our polymer science testing, Cincinnati is home to our state-of-the-art accelerated creep testing facility. Over 60 fully instrumented creep testing machines can apply controlled loading up to 100 kips at temperatures up to 2,000 degrees Fahrenheit. and that's plus or minus half a degree Fahrenheit, while measuring strains on the order of 10 to the minus 6 per hour, with the results expressed in both MPC omega and Larson-Miller parameters. In Houston, fatigue testing can include full-scale, mixed loading, have the effects of corrosion included, as well as a resonant bending fatigue testing. From over 6 million pounds to less than a gram, a full range of standard and customized tensile compressive testing can also be accommodated. In Waller, Texas, and in our Moore facility, burst testing up to 60,000 psi internal or 30,000 psi external, as well as other load testing, can safely be conducted.
Thank you, John. I'm going to describe here our materials and metallurgy capabilities. Failure analysis and material testing include the quantification of damage from creep as well as other damage mechanisms is integral to the assessing of mechanical integrity of equipment and components. Stresses routinely performs these activities for our customers as part of a fitness for service assessment or remaining life assessment to help them determine if a component can make it from one turnaround to the next. Failure analysis, understanding why material failed is as important as understanding why it succeeded. A large portion of the materials work that stress performs is directly or indirectly related to the failure analysis. Whether it is validating a material's performance in an environment through comparative testing or understanding why a material failed, Stress has state-of-the-art equipment along with experienced material engineers to perform that. From the material testing capabilities, we do full characterization of materials, which include chemical compatibility, aging and life assessments, creep and stress relaxation. In addition to that, we do a lot of accelerated creep and fatigue testing. And as John outlined before, we have over 70 creep frames in our lab. So here's some examples of some material testing we got. This slide shows examples of several material test methods used for evaluating materials. Fatigue testing, or what affectionately called bouncing beddings, is what you see here. This test is designed to determine the fatigue life of a threaded or welded joint by turning an eccentric weight, the yellow end effect that you see in the picture, and putting the pipe in its natural frequency. In addition, as we described earlier, you can see the over 70 creep frames in our lab here in Cincinnati. In addition, you see cyclic testing in order to test materials that are going in cyclic environments. And then there's the CTOD, crack tip diffraction, and also our lab in Cincinnati, which tests non-metallics as well as metallics with miniature samples. As we conclude this presentation, what I wanted to make sure of was to let everyone know that Stress is following RegAGAP and industry guidelines, which allows you to meet your safety and reliability objectives. Stress utilizes the following resources and capabilities to facilitate our analysis and assessments. We've outlined in the presentation today material characterization, full-scale testing, simulation and modeling, and most importantly, on-site testing and monitoring. Thank you for listening to John and I. We will stay tuned for your questions in just a moment.